This is Lesson 10 in Chapter 6. Today we're going to learn how to integrate using partial fractions and also long division. In our unit on integration, we found the integral of rational expressions such as this using the technique of U-substitution. Now we need a new approach to integrate rational expressions like these three examples, where the numerator is not necessarily the derivative of the denominator, or it's not the derivative in some form that's usable. In a proper rational expression, the degree of the numerator is less than the degree of the denominator. If the expression is an improper rational expression, the degree of the numerator is greater than the degree of the denominator, and we may have to use long division to put the expression into proper form. So let's consider a proper rational expression shown in the equation below. The expression on the right side of the equation is called the partial fraction decomposition. That's this part over here. When the process is completed correctly, we say that the fraction has been decomposed into partial fractions. So in an algebra class, if you added these two terms together, we would get the left side. The denominator is a product of distinct linear factors. For each distinct factor in the form of ax plus b, the sum of the partial fractions includes a term in the form where there's a constant in the numerator and that factor in the denominator. So just a special note here, for the BC exam, you're only going to be presented with partial fraction integration where the denominators contain non-repeating linear factors. So to begin the process, we will need to split the denominator of the integrand so that each part can be integrated separately. We simply need to solve the associated equation for the a value and the b value. So let's give that a try. If we want to integrate by the method of partial fractions, the first thing we want to do is to rewrite that expression as 1 divided by our linear factors, which is x plus 2 times x minus 2. And we want to create some number up here, some real number, where x plus 2 and some other real number, x minus 2, where these two terms total this amount. So I like to use the Heaviside method. And the Heaviside method has us multiply both sides by a common denominator. And then we solve for the a and b term using x values that create a 0. So here's what we mean by that. So if I multiply this equation 1, I'll have a times x minus 2 and the b term times x plus 2. So if we want to let x, let's let x equal 2 in this equation, the a term disappears. And 2 in the place of x here would give us 4b. So 4b equals 1. This tells me that the b value is going to be 1/4. And then to find the a value, we could let x equal -2, and that would zero out this factor over here. So if x is -2, then 1 is equal to -4a, and this term disappears, and that tells us the a term is -1/4. So after we find the values for the a and b terms, then we want to use the x values that create a 0 and then integrate accordingly. So next we want to integrate. So just to make sure that we're understanding this, 1 over x squared minus 4 dx has been rewritten to be negative 1/4 in the numerator divided by x plus 2 and positive 1/4 for the b term in the numerator divided by x minus 2, and we're integrating those two expressions with respect to x. So since the 1/4 is common here, drag that out here in the front, the integral of 1 over x plus 2 is going to be the natural log of the absolute value of x plus 2. And then pulling the 1/4 off of here, the same thing, the integral, the antiderivative of 1 over x minus 2 is the natural log of the absolute value of x minus 2 plus c. So this is integrating using the method of partial fractions. And this one we have x minus 11 in our numerator divided by x squared minus 7x plus 5. If we use the factors x minus 5 and x minus 2, negative 5 times negative 2 is positive 10, and negative 5 plus negative 2x is negative 7x. So we need an a value for the first factor, x minus 5, and we need a b value for the second factor, x minus 2. So using that method, we want to cross multiply or clear the fraction by multiplying x minus 11 times both factors x minus 5 times x minus 2, and then we'll multiply the a value times the missing factor x minus 2 and the b value times the missing factor x minus 5. So here we have, let's say in the first case we get rid of the 5. So if we let x be 5, then 5 minus 11 gives us negative 6. This term goes away. 5 minus 5 is 0 times b, and 5 minus 2 is 3a. So negative 6 is 3a. That tells us a is negative 2, and we found the a term. Next, we want to eliminate the a, so we'll let x be positive 2. And if x is positive 2, then 2 minus 11 is negative 9. And this 2 here eliminates that term, and 2 minus 5 is negative 3. So our b term is positive 3. So we've substituted zeros of the denominator on the left to find that a and that b. Right? We substituted the 0 here for 5 and the 0 here for 2, and that gave us the values of a and b. So next we want to integrate with a being negative 2 divided by x minus 5, and b is 3 divided by x minus 2, and we're integrating with respect to x. This gives us negative 2 times the natural log of x minus 5 absolute value, and positive 3 times natural log x minus 2 absolute value plus c. Now you can stop here, which is perfectly fine, but if it was a multiple choice test and you needed to find a combined term, that would look like the natural log of x minus 2, and we could put the 3 here or cube it here, and we would divide by x minus 5, and then that power would be squared. So the difference of the logs, the quotient of a log is the difference of two logs, and then plus c. So partial fractions. Here's one for you to try. You can turn your video off and come back to check your work to be sure that your work matches my work. So I'm getting factored form on the bottom, and we need a numerator, an A value, and a numerator for the second term, the B value. So if we eliminate the first term, x, with a 0, then we have 3x plus 6 equals A times x plus 3 and B times x. So if x is 0, you have 6 is equal to 3a, so a is 2. And we can go back up here, erase this. We found out our a value is 2. And then if we eliminate the other term with the -3, that gives us 3x plus 6. So x, 3 times 3, that's -9 plus 6. So -3 on the left is -3b, and our b value is +1. So now it's just a matter of finding that integral, because we're going to integrate these two terms. And just to save space, I'm going to erase this. So our integral turns out to be this partial fraction decomposition. And when we find the antiderivative, that's 2 times the natural log of the absolute value of x plus the natural log of the absolute value of x plus 3 plus c. And the log, the sum of two logs, is the product that should be absolute value plus c. So the product, make this look a little prettier, that should be x squared, absolute value, x plus 3. So we're multiplying that together and combining those logs. All right, in example 4, we're going to try a little different approach. We know that the numerator would factor to be a over x plus b over x plus 2 plus c over x minus 2. And we know that our zeros are going to happen when x is 0, when x is -2, and when x is +2. So we know these are the things, the 3 values that make our denominator 0. So let's start off with the first one. If x is 0, we have 0 squared plus 12 times 0 plus 12 divided by 0 plus 2 and 0 minus 2, since we're eliminating this factor. That tells us we have 12 in the numerator, -4 in the denominator, and our a value is -3. So we want to switch out our a value, which is now -3. Then moving on to the next 0, if x is -2, then we have in our numerator -2 squared plus 12 times -2 plus 12, and we're eliminating this factor, so we have a -2 times a -2 minus 2. And that's going to give us, let's see, this should be in parentheses, +4 minus 24 plus 12. So that looks like -8. And we've got -4 times -2, so +8. And now we know our b value is -1. So we'll replace that b with -1. And then finally, if x is 2, and we substitute for all the terms, we have 2 squared plus 12 times 2 plus 12. So 24 and 12, that's 36. And 4 more would be 40 in the numerator. We've eliminated this term, so we have 2 for the x and 2 plus 2, which gives us 4 times 2, that's 8. So our c value is 5. Now we know what our integrand looks like. So this is going to be our integrand in terms of x. And again, I'm going to erase this for saving space. Okay, so integrating after we found our partial fraction decomposition gives us our antiderivative of -3 natural log of x minus natural log of x plus 2 plus 5 times the natural log of x minus 2 plus c. And again, like I said, you can stop here or you can combine using the rules of logarithms. So we would have x minus 2 to the 5th power divided by x cubed, since that's a negative exponent, times x plus 2. And all of that plus c. Now let's take a look at long division, because like I said, if we have an improper rational expression where the degree in the numerator is larger than the denominator, we need to use long division to write it in proper form. So in this case, I'm going to look at the -4 as my 0 in the denominator. And even though they say long division, I'm going to use synthetic division for space here. So bringing down the 3, we have -12. 8 minus 12 is -4. Times -4 is 16. -10 plus 16 is 6. And 6 times -4 is -24. And we have a remainder of -9. So we can rewrite our integral to be 3x squared minus 4x plus 6 plus the remainder -9 divided by x plus 4, and integrate that in terms of x. So this antiderivative is x cubed. This would be minus 2x squared plus 6x, and then this would be a natural log, minus 9 natural log x plus 4 plus our constant. So that wasn't as bad as it seems. Example 6, same thing, just different. This time we're going to use long division. 2x minus 2 divides x minus 5. So 2x divides x 1/2, and 1/2 times 2x is x, and 1/2 times -2 is 1. And we want to subtract that from the term above, so this eliminates, and -5 minus 1, -5 plus 1, is -4, which makes our integrand 1/2 minus 4 divided by 2x minus 1. I'm going to factor that bottom out in terms of x. So if we take the 1/2 out, this would reduce down. Let's see, we could have 1/2 x, and this could reduce down to 2, and then that would be minus 2 natural log x minus 1, And if you wanted to go one more step, we could say that's 1/2 x minus natural log of the quantity x minus 1 squared plus a constant. This one, we're going to use long division. I'm using synthetic as we go, so x cubed and no x squared and 1x and no constant term. So we need 2 placeholders. Using synthetic division, this is 1, this is 1, and 1, that's 2, and 2 times 1 is 2 with the remainder. So our integrand is going to be x squared plus x plus 2 plus 2 divided by the divisor x minus 1. And then we're ready to go. So we have 1/3 x cubed plus 1/2 x squared plus 2x plus 2 times the natural log of x minus 1. So I'm taking this 2 from the numerator, placing that up there, so then we don't need absolute value bars, and adding our constant to the end. And here's one for you to try. Turn off the video and give this one a try. Come back and check your work. So if you used long division, you ended up with your integrand being 2x minus 3 plus x plus 11 divided by x squared plus 2x minus 3. And I don't know if you can see it from here, but this is going to be an issue where we need partial fractions. So we can integrate and get 2x minus 3, and using the idea of partial fractions, so we've got x plus 11 has to be an a number over x plus 3 and a b number over x minus 1. That's the way we're going to get x squared plus 2x minus 3. And employing your values for a times x minus 1 and b times x plus 3, and that has to equal x plus 11. So if we let x be 1, when x is 1, we end up with 12 is equal to 4b, so b is 3. And if we let x be negative 3, then we have 11 minus 3, and then negative 3 minus 1, that's negative 4a, so our a value is 2. And that gives us a negative 2 over x plus 3 and a positive 3 divided by x minus 1 for our partial fraction decomposition. So let's just erase this here. And then when we integrate, we'll have x squared minus 3x minus the natural log minus 2 natural log of x plus 3 plus 3 natural log x minus 1 plus a constant. And then we just have 2 more challenging ones to take us to the end. So here in number 9, we're going to use U-substitution, and let's let U be cosine of x, then du is negative sine x dx, and that way we can use partial fractions. So we have, if u, let's see, if u is 0, then we're going to have -1 over u times u plus 1. Got a over u and b over u plus 1. And the way I got that is to think about our integral is negative du over u times u plus 1. So using this with our u substitution. And we want u to be 0. So if u is 0, then a is -1. If u is -1, and we cross multiply, then b is +1. So we have our a value and our b value, and then we're ready to integrate. So our a value is -1 and our b value is +1, and we want to integrate. So this is going to be the integral of -1 over u du, and that would be negative natural log absolute value of u, and this one would be natural log of u plus 1. And if we substitute back, our u value is cosine, that's negative natural log cosine of x plus natural log cosine of x plus 1 plus c. And again, I'm going to neaten that up to use the log properties. We've got natural log cosine of x plus 1 divided by cosine of x plus c. And actually we could put that whole term in absolute value and make it just one concise expression. And last but not least, we're going to look at this one and let u be e to the x. And then du is e to the x dx. So our integral would be du in the top and u squared minus 1 in the bottom. So for our partial fractions, we have 1 in the numerator, u plus 1 times u minus 1, and we need an a value for u plus 1 and a b value for u minus 1, and 1 is going to be a times u minus 1 and b times u plus 1. So if we do this with the Heaviside method, if u is -1, so if u is -1, then a is -1/2, and if u is +1, then this goes away and b is +1/2. So our integral will be -1/2 u plus 1 and +1/2 u minus 1 with respect to u. So we have -1/2 natural log of u plus 1 and +1/2 natural log of u minus 1 plus our constant. Our u value was e to the x, so I'm going to take out the 1/2 natural log, and that would be e to the x minus 1 for this numerator divided by e to the x plus 1. This is always positive. That needs absolute value bars. And we are done. Okay, because we know e to the x plus 1 is positive for all x. That's the end of our lesson.